And we're back. Welcome back from the weekend and happy Tuesday. Today, we will switch gears a little bit and look at a distribution that makes use of the geometric distribution, namely the negative binomial. We'll also talk about something called Petersburg's paradox. But before we begin, some administrative bits. You should be caught up on the reading by now, pages 57 through 67 in the Barron text Probability Statistics for Computer Scientists, namely section 3.4. Please get caught up if you have not done so. So where we last left off, we proved the expectation and the variance for the geometric distribution. So let's play a little bit of a game. Ready? Steady? Okay, let's go. So let's play a game, and in this game, it will proceed over a series of rounds. And each round is going to be independent of the other, so that means the outcome of one round is not going to influence the outcome of the subsequent round. And for a given round, you're going to wager some amount. Let's just call this X. It doesn't matter what X is. It could be $1, it could be $100. But you're going to wager some amount. Now, you can either win what you wagered. That means you gain X amount of dollars and you're happy. Or you lose X amount of dollars, so you gain negative X dollars, and you're not very happy about it, quite sad. Now, it doesn't matter how favorable your chances are for winning a given round from one round to the next. It doesn't matter if the probability of winning for a given round is very small or it's a very large probability. Now, what if I were to tell you that I can guarantee that you will win, that you will make a profit? Guaranteed. And it's not trickery. Well, it's just a little bit of mathematics. And you might be thinking, gosh, well, how can you do that? It doesn't matter what the probability is. How can you do this? So let's follow this algorithm. You first decide how much profit you desire. Well, isn't that wonderful? Let's say you wanted $100. You want a profit. You want to be up $100. The only caveat is once you win, you stop, right? Don't get greedy. You just stop once you've won. And I can guarantee that you can decide what type of profit you want. So let's say you chose $100. You bet $100 on the first round. If you win, you stop. Okay. What happens if you lose? Okay, if you lose, you double your wager for the next round to 200, 400, 800, etc. Then you bet this new wager, and you go back to step 3. Did you win or lose? You stop if you win. If you lose, you keep playing. Now, what I tell you is that once this algorithm halts, you will be up, guaranteed, $100. Don't believe me? Try it out for yourself on a piece of paper. So let's take a look at the structure of this problem. What type of distribution describes a single round? We have two-way outcomes, win or lose, and each round is independent from one another. And the other question is, what type of distribution describes the number of rounds you play? You keep playing rounds until you get a single success, and then you stop. And so you have successes and failures for each round, and they're independent from one another. And for the number of rounds you play, each round has a success or failure. They're independent from one another. You keep playing until you get your first success, your first win. So you have a sequence of failures ending in a single win or success. And so the individual rounds, they're Bernoulli trials. And the number of rounds you play before you get your first success, that's a geometric distribution that describes that. And so when we look at this game, we need these tools, specifically the geometric, which is just a sequence of a particular set of Bernoullis, a bunch of failures ending in a single success. So one of the questions then, on average, how many rounds will this game last? Now, of course, that's just the expectation of this geometric distribution. And so if the expectation is 1 over p, if you have a 0.125 or 12.5% probability of given round, then that's 1 over p, that's 1 over 0.125, which is 8 rounds on average, the expectation. And so one of the strategies that we look at when we try to analyze some quantity from this, like how much money do you need to play this game? Because it doubles the wager every time you fail. So it's reasonable, well, do I have enough money to pull this off? So let's think about our strategy here. For each round, the desired profit amount that you can win, it doubles. And so mathematically, successive doubling is like saying you're going to take 2 and you're going to exponentiate it to some power. Now, that's the doubling function. And the desired profit that you have, you want to get $100 profit at the end. And so let's comprise what I'll call the money function. And this function y is the amount of the last bet that you're going to make. And in fact, if you keep losing x minus 1 many times, and that last time is a success, you walk away. So the amount of money that you have of the last bet where you lost is going to be some money function, I'll call it, 100, the amount of profit, times the successive doubling, times 2 to the x minus 1 power. And so if it's the first round, it's 2 to the 0 power, and that's 100. If it's the second round, that's 2 to the 1 power, so that's 200. Then 2 to the 2 power, that's 100 times 4, that's 400, etc. So this is going to describe our money function, what we're calling our money function. And so now what we want is the probabilistic average for this money function. Now this money function, the number of rounds until success, that's a geometric distribution. So we're going to use the probability mass function to compute the expected money function corresponding to this game that we're playing. And so here, our money function, expectation, we have the probabilistic weighted average. And so here we have the money function, that's our y, 100 times 2 to the x minus 1 power. For all number of rounds x, this is the amount of money that you have to have, because you're going to lose that amount of money, over each one of those rounds x, times the probability of x, the round number. And so the money function that you have, remember on the last round, you're not going to lose that money, but all of the rounds up to and not including the last round, x, you're going to lose that money, but round x, you gain that money. So we take the probabilistic weighted average, our money function, times the probability of a particular number of rounds, where that round x is the round where you win. Okay. So let's compute the expression for this. And for this, we're going to use the probability mass function for the geometric distribution. Now remember, we had a sequence of x minus 1 failures. So these are our failures. And then that ends in a single success. This is our success at a rate of p. So this is going to be our probability. We substitute, and we get the expression expectation of x, the number of rounds where we have some number of our first success, where we walk away, times this money function is how much money we need to have. So we have our sum, index over x, 100 times 2 to the x minus 1, times 1 minus p quantity exponentiated to the x minus 1 times p. Okay, so we can pull out this 100p because that's a constant under the summation. Our index for that summation is x. And we'll now collapse the 2 to the x minus 1 into the same parenthesized expression as the 1 minus p. And we have a single exponent, x minus 1. And so we're going to take this quantity, and now we're going to have a change of the index. We're going to say let k equal x plus 1. So if k is equal to x plus 1, we say k is equal to 0 as the starting index, and k is equal to infinity, final index. And we just write k as our replacement for x minus 1. And this is our new expression. 100p times summation, k goes from 0 to infinity, of quantity 2 times quantity 1 minus p, all exponentiated to the k power. Now, this might look familiar. That looks like our geometric sequence, and it is a geometric sequence. But we're going to imagine then that this is our constant factor that we called r, and we're going to assume that r is going to be less than 1. Now, of course, it could be greater than 1, depending on what the value p is, but let's just assume it's less than 1 for now, and then we'll talk about that case where it's greater than 1, okay, or equal to 1, greater than or equal to 1. All right, so if this quantity, constant factor for geometric series, r, is less than 1, well, using the fact that we proved before for the closed form expression for the geometric sequence, that's 1 over 1 minus r for r less than 1. So if that's the case, then we write 100b times, we substitute for this expression, 1 over 1 minus our r, which is 2 times 1 minus p parenthesized in the denominator. And so if we do that, we get this expression, and then we do a little bit of algebra in the denominator, and we get 100p, the numerator, upon 2p minus 1 in the denominator. Okay, so let's write this out. And for the case where this constant factor defining the geometric sequence r is less than 1, well, we get this expression that we just solved for, 100p upon 2p minus 1. Now, if p is less than equal to 1/2, we have the case where r is greater than equal to 1. So why is that? If p is less than or equal to 1/2, well, if p is exactly equal to 1/2, that's 1 minus 1/2 is 1/2. 1/2 times 2 is 1. And then we're having a factor of 1 added an infinite number of times, and that's going to be an infinite quantity. If r or p is less than 1/2, that's for p equals 1/2. If p is less than 1/2, well, 1 minus something that's less than 1/2 is something that's greater than 1/2. If you have something that's greater than 1/2, 2 times something greater than 1/2 is going to be greater than 1. And you have something greater than 1, you're adding together an infinite number of times. That's also going to be infinity. And so this quantity here, it can be an infinite expectation, even though the quantity, the random variable we're talking about, our money function, is finite. And this is one of those weird things in probability. It's called St. Petersburg Paradox, and it talks about this idea of utility, this long-term benefit or long-term in terms of expectation for making certain decisions. Okay, so in the book, they are not correct when they solve for the geometric sequence for the convergent version for which this constant factor r is less than 1, and that corresponds to the case where p is greater than 1/2. And so please take a look at this version and put a note in the book on a slip of paper, say, hey, wait, there's something wonky going on there. Look at this version, which is exactly how you solve for the convergent version, the closed form expression for the geometric series. Okay, so let's move on and let's look at another related distribution related to the geometric. And this is called the negative binomial. So we have a scenario. We have a sequence of independent Bernoulli trials, and this could be flipping a coin, for example. And as a Bernoulli trial, you have two-way outcomes. One is called success, the other is called failure. Now, this negative binomial measures the following. What is the number of trials that you need in order to obtain k successes? So you have n many trials, trial 1, trial 2, trial 3, trial 4, and so forth, up to and including trial n. And so what it's asking, you have some number of trials, and you want to know at what point, at what trial, we'll call that trial number x, do you have k successes? And so here we have success or failure, success or failure, success or failure. You might not get k successes at the first k trials that you try, but at some point, we call that trial X, you're going to have k successes. So you have some interleaving of success and failure, success, success, failure, 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 success, success, failure, and you want to know at what point are you going to have k many successes. And this is related but not the same to the binomial. This is called the negative binomial. Now, the binomial, it says if you have n many trials, so the number of trials is fixed, what's the probability of getting k successes? Here, the quantity of interest is not the number of successes, it's the number of trials, the number of trials you need to get k successes, not the number of successes in n trials. Okay, and so let's take a look at this. So let's say that trial where you get the k success is trial number X. And at some point when you start out, let's say the first position, could be the second position, you're going to get the first success. And so somewhere in this set of trials, trial 1, 2, 3, 4, all the way up to trial X, you're going to have a total of k successes where the k success is on trial number X. So that's really important to the structure of the problem. So if that's the case, there's a structure to this. The trial that comes before trial X, well, that's going to be the X minus 1th trial. So you have trial 1, trial 2, trial 3, up to, and including trial number X minus 1. X minus 1. That should be an A, trial X minus 1. And so we need to identify the trials that precede trial number X. So that's trial 1, 2, 3, up to and including the X minus 1th trial. And one of the things we want to know then, if you have the k success that you observe on trial number X, how many successes do you have scattered among trial 1, trial 2, trial 3, up to and including trial number X minus 1? So if you think about it, if the k success is achieved on trial number X, that means that you must have had k minus 1 successes scattered somewhere about these first X minus 1 many trials. So k minus 1 successes are scattered among these X minus 1 trials. Okay, so does the order matter for these k minus 1 successes? No, it does not. You could have success, 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 k minus 1 many times, and then followed by failure, 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 all the way until that last failure is on trial X minus 1, and then you have that k plus that k success on trial X. You could also have all failures, and then you have k minus 1 successes right before you have that k success. So the order does not matter, absolutely not. So if that's the case, well, the rate of success is called P, probability P. Well, the rate of failure, law of total probability, tells us it's 1 minus P because you have two alternatives for each trial. And so that means you have a total of X minus K failures. So these are your failures. And you have a total of K successes at a rate of probability P times P times P, K many times. And these are your successes. Now, if you have X trials, and in these X trials you have K successes, that's P to the K for that rate, and 1 minus P, or synonym for that, Q, we'll nickname it Q, to the X minus K, is the probability of all the failures, because that's 1 minus P times 1 minus P times 1 minus P, X minus K many times. Now, certainly, because the order doesn't matter, we're going to do selection, and we're going to do this selection in indistinguishable number of ways. So we're going to use X minus 1 is the number of trials right before that X trial. And in there, you're going to select K minus 1 of them for the placement of those successes. And so we multiply that by 1 minus p to the x minus k, those are for the successes, and p to the k, those are rather 1 minus p to the x minus k, those are the failures, and p to the k, these are the successes. And so we're using this x minus 1 choose k minus 1 to account for all of the different arrangements, indistinguishable arrangements you can have for these x minus k failures and k successes. All right, so if we look at this, this is our probability mass function. The probability of trial x being the one where you obtain k successes is x minus 1 choose k minus 1 times 1 minus p quantity to the x minus k power times p exponentiated to the k power. Likewise, this probability, p of x, you can think of it as the probability that the xth trial results in the kth success. Or it's the probability that you have k minus 1 successes scattered among the first x minus 1 trials, and then the last trial is a success. And that last trial being a success is very, very important. All right. And so if we think about this, well, if we have a random variable x, and this represents the occurrence of the first success, and we have random variable k for the kth success that happens on trial x, the xth trial in the sequence of some number of trials, well, let's look at this random variable x. Well, we have a failure, 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 ending in a success. Failure, 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 ending in success. And so here's the first success. And then after that, the next trial, we start another set of rounds, failure, 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 ending in success. And then after we have that next success, we keep doing it again and again and again until we have failure, 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 ending in the success. That last success is on that trial that we're calling trial number x. And so each one of these trains or sequences of failures ending in a success is exactly a geometric distribution. And so this is the first geometric distribution. This is the second geometric distribution. The next success is the third geometric distribution. And that kth success is the result of a kth geometric distribution. So we can describe a negative binomial as a geometric distribution, the concatenation of k many of these geometric distributions. Okay, so we write it, some variable x is a negative binomial random variable. It's distributed as, that's what this squiggle means, distributed as random variable x is distributed as a negative binomial where you have k successes given a probability on each trial of success of p. Well, that's the probability that trial number x will be the trial where you have that k success. So the mass function, probability of x, x minus 1 choose k minus 1, times our failure rate, 1 minus p to the x minus k, times the success rate, which is p to the k power. Now, of course, we know from before that the expectation of a geometric random variable is 1 over p. So if we have k of them, it's k times 1 over p. And we know from linearity of expectation, if you multiply k times a random variable, so this random variable is geometric with probability p. Now, to make this geometric into a negative binomial, we just say k, some constant, times x. So if we want the expectation of kx, that's just k times the expectation of x, linearity of expectation. And then we write k, this expectation is 1 over p, and there's our k over p. Likewise for variance, well, we said that the variance of some constant times some variable is equal to k squared times the variance of that variable. And this is geometric. Well, how do you get a negative binomial? It's just k times that geometric. So that's variance is k times 1 minus p over p squared. We have k many of these variances. So kx, you could also think of this as x plus x plus x k many times. So that's just 1 minus p, the variance of a single variable, p squared. You're going to add it up to itself, 1 minus p plus 1 minus p, 1 minus p over p squared, k many times. That's k times 1 minus p upon p squared. Okay. All right. So this is our variance of the negative binomial, and this is our expectation of the negative binomial, and it's related to the geometric. You have a sequence of k many geometric distributions, random variables, and that is collectively your negative binomial. All right. So with that, we're going to end there. That's all I have. It's a relatively short one. Please make sure you're staying up on the reading. And next time, we will examine the Poisson distribution. Now we're going to take this two-way outcome, our Bernoulli, and we're going to have it occur as a sequence in time. So with that, as usual, please stay healthy, stay safe, and I will see you on Thursday.